Good morning, class. Welcome to today's lecture. We'll be talking about electrodynamics of charged particles. But before then, let's try to remind ourselves on some things we have learned before. We should always remember that stationary charges possess electric field. Stationary charges possess electric field, just like we have in the first class, where we say maybe a positive charge would have electric lines of force directed radially outwards. And electric charges can exist as monopoles, that is either positive or negative. Third, electric force acts on a stationary charge. We have spoken about that during talking about Coulomb's law. And electric force acts along the direction of the electric field, just like the lines of force here, the line of force here. Electric force acts in a straight line, connecting both two charges together. So electric force acts along the direction of the electric field. And electric force acting on a charge Q in electric field E is related to F equals to QE. Electric force F acting on charge Q in electric field E is related as F equals to product of Q and E. So that is, electric force is product of charge and electric field strength. So the new things we should now add to what we've known before is that when electric charges are in motion, they possess magnetic field in addition to their electric field. We know electric charges, when they are at rest, they possess electric field. But once the charge bodies set in motion, once they are in motion, in addition to their electric field, they begin to manifest magnetic properties. They begin to show out, they possess their magnetic properties is shown. And in short, they have magnetic field when they are in motion. The direction of the magnetic field is perpendicular to the direction of motion of the charge. That simply means that when the charge is in motion, let's say it's moving in this direction, the direction of magnetic field will be perpendicular. We usually use B to represent magnetic field. So when the charge is in motion, when it's having a velocity V, then the magnetic field, which is also a vector property, will point in a direction that is perpendicular to the direction of motion. So I want us to take our time to digest the rudiments, which is electric charges. They possess electric field. But when they are in motion, they manifest magnetic properties. 1 minute, please. Sorry for the break. I had power outage, right? Okay, so like I was saying, electrons or electric charges can be at rest and they possess electric field, but once they set in motion, in addition to their electric field, they now exhibit magnetic properties, thereby possessing magnetic field. And the direction of this magnetic field is perpendicular to the direction of motion of the electric charge. The direction of the magnetic field is perpendicular to direction of motion. And as we know about, I don't need to embarrass you, but at least you must have heard of magnets before or seen magnets before, where it's usually like a bar, you have a North Pole, South Pole. Whenever we have a magnet, it is always having both poles. A magnet would have North and South Pole. It cannot just say this magnet is a North Pole and that magnet is a South Pole. It's not possible. So they cannot exist like we have in electricity, where electric charges can be either positive or negative. So in magnetism, magnets exist as dipoles. Magnetic force may act on a moving charge, but cannot act on a stationary charge. Just like I have said, when the charge is in motion, it possesses magnetic field. For the fact that it now has magnetic field, then it will respond to other magnetic fields. It means that it can behave like a magnet. And when magnetic force acts on it, it responds. But when it's in motion, but when it is stationary, the velocity is zero. When it's stationary, there cannot be any magnetic property, and magnetic force will not act on it. So this just like we have in electric field and electric field lines, this is a magnetic field lines, where the lines emanate from the North Pole and terminate at the South Pole. So they have similar properties like the electric field lines. So let's move forward. So the magnitude of the magnetic force exerted on the charged particle is proportional to the magnitude of the charge and the speed. Like I said earlier, we have if we have okay, let's clear this. If you have a charge traveling in this direction with velocity v, it will possess a magnetic field, and the magnetic field will be perpendicular to the direction with which the charge is traveling. So if it's a positive charge and the magnetic field points to the left, then if it is a negative charge, the magnetic field will point to the right. And the magnetic force that will be experienced depends on the velocity of that charge. So if it is moving very fast, you would expect a greater magnetic force. And if it is a charge that is having a higher magnitude, you would also expect a larger magnetic force. When a charged particle moves parallel to the magnetic field vector B, when a charged particle moves parallel to the magnetic field vector B, the magnetic force on the particle is zero. What that means is that let's represent this, let's have a wide screen. If we have a scenario where we have magnetic field in this direction, and we also have an electron, let's say for instance, traveling also in this same direction. Let's say we have an electron traveling in this direction. This particular electron will not experience any magnetic force because this fine, it possesses magnetic field and it's traveling in another magnetic field. But for the fact that it's traveling in the same direction with the magnetic field, it's traveling in the same direction in another magnetic field, it will not experience magnetic force. So for magnetic force to be experienced by a charged particle in motion, there should be a component of that motion that will be perpendicular to the magnetic field. There must be a component, at least a component, or let me say it in this way. If the electron which is traveling in this direction, like I said, the magnetic force will be zero. If the electron now travels in this direction, which is perpendicular to the magnetic field, you will experience, the electron will experience magnetic force. If the electron, another electron, decides to travel in this direction, it will also experience magnetic force, but the magnetic force that the electron that travel on the green path will experience will not be as large as the electron that traveled through the black path. While the electron that traveled through the red path will not experience any magnetic force because the direction of its travel is parallel, or it's the same as the direction of the magnetic field in which it is traveling. So there should be a component of that motion that will be perpendicular, the components of that motion that will be perpendicular to the direction of magnetic field. So let's move forward. The magnitude of magnetic force exerted on a moving particle is proportional to sine u, where u is the angle the particle's velocity vector mixed with direction b. Let me try to put that like a diagram. When we have, well, let me go back to color blue. Let's represent our, okay, let me take it. Let's take these blue lines to be direction of our magnetic field. Direction of magnetic field. And let's also take another red line to be the direction with which a charged particle is traveling. Let's call this 1. Let's call this 2. And let's go 2. And let's call this 3. If you look at 1, the first one, number 1, it is forming an angle, let's say 90 degrees with the magnetic field. So we can say for 1, sine 90. For the second one, which is number 2, it is forming, it's in the same direction with the direction of magnetic field. So we can say that is 0. The angle between the line number 2 and B is 0. So we can say sine 0 degrees. And the third one is forming an angle in between 0 and 90. Let's just approximate it to say sine 45 degrees. So what the grammar here is telling us that the magnitude of the magnetic force exerted on a moving particle is proportional to sine u. So that means as Sin U increases, the magnetic force will increase. And what is sin 90? That should be 1. What is sin 0? That should be 0. And what is sin 45? That should be 1 over root 2 also. 1. So you can see that as the angle tends towards 90, as the angle between the direction of motion of the charged particle with the magnetic field, as they tend towards 90 degrees, will have the largest magnetic force experienced on that charged particle. So this is the formula that we've been talking about all along. FB here is the magnetic force. The magnetic force is equal to charge Q, product of charge Q and velocity vector and with a cross product to magnetic field. This is not ordinary multiplication. This is vector multiplication, vector cross product. And it's not the same thing as the normal multiplication you have, because we are having two vectors and we have decided them to multiply them to get another vector. Because when you are multiplying the two vectors to get another vector, what you do is cross product. And this can also be simplified to as we saying Q B sine theta. You should have learned this from maths department. So, and it simply shows that when theta is 0, when the angle between the velocity and the magnetic field is 0, then the force will be 0. But it will be maximum when they are perpendicular to each other. And this is just this expression here is representing the images we have here. This positively charged particle is traveling on this red line, and there is a magnetic field. There is a magnetic field pointing to in this green line. Then it will have a magnetic force that will be perpendicular to both magnetic field and the velocity of travel. So one beautiful thing about this expression is that we will only have magnetic force when there is a vertical component, when there is a perpendicular component between the velocity of charge travel and the magnetic field. And even at that, the magnetic force will be perpendicular to both of them. So the magnetic force, the direction of travel, the velocity of travel of the charged particle, and the magnetic field, direction of magnetic field, when they are perpendicular to each other, that's when we have the maximum magnetic force. So still on our many stories for today, comparing electric force with magnetic force. The electric force is along the direction of electric field, while magnetic force is perpendicular to the magnetic field. The electric force acts on the charged particle regardless of whether the charged particle is moving, whereas magnetic force acts on the charged particle only when the particle in motion has perpendicular components to the magnetic field. Sorry, this should be field, not force. To the magnetic field. The electric force does work in displacing a charged particle. The electric force does work in displacing a charged particle, whereas the magnetic force associated with the steady magnetic field does no work. So you can see electric force, magnetic force, they are both forces, they are both vector quantities, but they have their unique properties. They have conditions where they can be experienced. So let's move forward. So let's talk about the motion of a charged particle in a uniform magnetic field. We should have known from mechanics, introductory mechanics, that magnetic force, F sub B, is equal to, or just like force, force is a product of mass and acceleration. And we know that acceleration, or let me say angular acceleration, is v square over r. And mass times acceleration, when we multiply both sides of this expression with mass, we have ma equal to mv square over r. And since ma is equal to fb, then that means the expression we have here is same as fb. And from the expression we had in the previous slide, fb equal to qv cross b, then we can still come here to say fb equal to qv cross b. If v and b are perpendicular to each other, then it's as good as qvb, and that is why we have fb equal to qvb here. So since this expression is equal to this expression, then they are now equated right here for us to now have mv over qb to be equal to r. So this is one of the expressions we'll be using very soon. And from this expression, we can obtain v over r. Our v over r, as shown here, will be equal to qb over m. And v over r is equal to angular velocity. So let's move forward. Okay, so let's look at this diagram before moving forward. This diagram, looking at this diagram, we have a charged particle here, a positively charged particle is moving with velocity v. It's moving with velocity v for the fact that it is in the presence of magnetic field. The magnetic field, imagine as you are looking at your screen, that you are beaming magnetic field onto this photograph. That means that the direction of magnetic field is pointing into your screen. As the direction of magnetic field is pointing into your screen, that means that the direction of that magnetic field is perpendicular to this positive charge. It is also perpendicular to the direction with which this positive charge is moving, rather. You are looking into your screen and you are assuming that you are beaming magnetic field into the screen. The direction of the magnetic field you are beaming into the screen is perpendicular to the direction with which this charged particle is moving. So therefore, you should expect the charged particle to experience magnetic force. And the magnetic force that will be experienced will be mutually perpendicular to the direction of magnetic field and also to the direction in which the charged particle was traveling. So this is the magnetic force. As you can see, the direction is perpendicular to you imagining a line entering your screen. And the direction of this magnetic force is also perpendicular to the direction with which the charged particle was moving originally. So now the charge particle was moving in this direction, right? But something is pulling it leftwards. But the fact that something is pulling it leftwards, it is going to bend. It will be unable to move straight. It will begin to curve. And that force keeps pulling it. It wants to go away, it keeps pulling it. Then it begins to orbit this axis. So just like we have the Earth moving around the moon, we said it is balancing one centripetal and centrifugal force. The same way, the magnetic force here is acting like a centripetal force, while the original direction of motion of that charged particle is the centrifugal force, which is now balanced by the charged particle moving around this circle. So from this expression we have here, where we have said omega equal to V over R equal to QB over M. I've just rewritten this expression so that we just see it right here. Oh, now I can't even see it. Okay, the previous expression was omega equal to V over R equal to QB over M. So from this expression, you can say your omega is equal to 2 pi f. And you can say f, which is frequency, is equal to 1 over period. And from that, omega will be, from that, omega will be 2 pi over period. So from that, we can now substitute and make period subject of the formula. Then we have the entire expressions we have here. So from these expressions, it is obvious that the angular speed of the particle and the period of circular motion does not depend on the speed of the particle or on the radius of the orbit. So this is the period, that is the time it takes this charged particle to move around this orbit. The time it takes, that's period, just like we've known in the previous periods, whenever we talk about periods in science. The time it takes to move around does not depend on the speed of the particle. And what does it depend on? It depends on the mass, the charge. It depends on the magnetic field that is applied. And this angular speed is known as cyclotron frequency, because charged particles circulate in this type of angular frequency. And this type of accelerator is called cyclotron. So a cyclotron is used to cause charged particles to orbit, to move in a circular motion of this nature. So this is an example that says that, this example is saying that a proton is moving in a circular orbit of radius 14 centimeter in a uniform 0.3 Tesla magnetic field perpendicular to the velocity of the proton. Find the speed of the proton. Find the speed of the proton. So that we can, from our previous equations, we can easily say B is equal to mv over qr. And what we need here is find the speed of the proton. We need v. That means v is equal to bqr over m. And we know our b to be equal to 0.35. We know our q to be charge of the proton, that should be 1.672 times 10 raised to power minus 27 kilogram. And radius, 14 centimeter. That's 0.14 meter. Oh, sorry, I made a mistake. After B, the next one is Q. Q is charge. Q is charge. Charge of the proton is, I put down the mass instead of the charge. The charge is 1.6 times 10 raised to power minus 19 coulomb. And R is the radius of the circular orbit, which is 0.14 meter, divided by mass. Then now mass of the proton, that is 1.672 times 10 raised to power minus 27. So whatsoever you get from that, easily you get the speed of the proton. Force on a charged particle in the presence of magnetic field, like we've seen before, is F subscript B force, that is magnetic force, is equal to cross product of QV and B, where V is the velocity vector and B is the magnetic field vector. And like we've learned also before, and we reminded ourselves today, the force on a charged particle, the electric force on a charged particle, is the product of the charge and the electric field. So when and we should know this vector quantity, and being vectors, we can add vectors easily as long as we're adding them. We're adding components that are alike. As long as we're adding them together, we have the sense. So now, when a charged particle is in the presence of both electric and magnetic field, in the presence of both electric and magnetic field, then we should just simply add the FB and the FE together, and that will give us the electric field plus the magnetic field, and that is known as Lorentz force. So we have applications of electrodynamics, and one of which we have before us now is a velocity selector. So the velocity selector helps in producing charges that have the same velocity. So whenever there are stream of charges and you want to filter out the particles that have velocities that are different from what you want, then a velocity selector is what you need. The velocity selector, like we have here, it's having the magnetic field directed into your screen. Just like you are looking into your screen, that is the direction with which the magnetic field is being, an external magnetic field is being applied to the velocity selector. So, and these two plates here, this is a positive and a negative charge plate, so it makes electric field to be directed, E to be directed from the left to the right of your screen. So now we have electric field pointing from left to right. And we have magnetic field perpendicular to that electric field beaming into your screen, the way you are looking at your screen. And now you now have a charged particle leaving from this source, going through this slit and going through this velocity selector. For the fact that the charge is in motion, it will possess magnetic field. For the fact that it possesses magnetic field and now it is entering another magnetic field, that means it will respond to that magnetic field. And how is it going to respond? It will respond by move in a direction that is perpendicular to its direction and also to the direction of the applied magnetic field. So because the magnetic field is applied looking into your screen, the charged particle is moving upward in your screen, and the perpendicular way to go is either to move left or move right. Well, for this illustration, it is assumed that the charged particle will move to the left as a result of presence of magnetic field. So because of the presence of magnetic field, that is why the charged particle is moving to the left. But we should also remember that these are charge plates, these are electric field sources, that is, the electric field is emanating from the electric field lines emanating from the positive plate to the negative plate. So that means that for the fact that we are talking about electric field, it means that the charged particle should be prepared to experience electric force. And the electric force it will experience will be in this direction of electric field. The electric field, F subscript E, so the electric force, F subscript E, is points in direction of electric field. That is one of the properties of electric fields we've learned before. The electric force points in direction of electric field. That is established. The magnetic force points in a direction that is perpendicular to the direction of motion of the charged particle and also the direction of the externally applied magnetic field. That's also, we know. So the strength of the magnetic field, B, and the electric field, E, can be adjusted such that F, the magnetic force, will equal to the electric force. And before you can balance that, when you are balancing that, you are balancing it with respect to a certain velocity V. When you are trying to balance electric force with magnetic force, you are balancing it with a certain velocity V. So the certain velocity V of interest, the certain velocity V of interest, the certain velocity V of interest will go through this point. It will experience magnetic force to the left. It will experience electric force to the right. But since it is the actual V of interest, the magnetic force acting on the left will be equal to the electric force acting on the right. Since both are equal, then it will keep moving on straight, undeflected. It will travel through straight, undeflected. If the velocity is larger than the desired velocity V, like I said, the magnetic force is this is designed for a certain field B such that the magnetic force is made to balance the electric force for a certain velocity V. If this certain velocity V is exceeded, the velocity is considered in determining magnetic force. So if a particle of higher velocity is traveling through, then the magnetic force that will act on it will be larger than expected. And when the magnetic force acting on it is larger than expected, that means for that particle that is traveling faster, it will have a greater magnetic force compared to electric force. That means it will bend towards the left and crash into the left plate here. It will not go out undeflected like the first scenario we had. Another scenario is when the particle entering into this velocity selector is slower than the desired velocity why this selector was designed. When it is moving through with a slower velocity, like we know, as like I've said umpteen times, magnetic force depends on velocity. If it is moving with a smaller velocity, if it is traveling slower than expected, then the magnetic force that it will experience will be smaller than the previous scenarios we've had. So since it is going to have a smaller magnetic force, that means that the electric force will exceed the magnetic force, and it will pull it will make the charged particle to travel, to curve and crash into this right plate, because it is traveling sluggishly than expected, and thereby losing, not having sufficient magnetic force to balance the electric force and move undeflected. So once it is traveling sluggishly, FB reduces, FE remains constant. FE is not bothered if you are traveling or not traveling, talk less of if you are traveling faster or slowly. FE is constant. FE depends on the potential difference between these plates. That is what FB, wants. So as long as FB is smaller, then FE will be greater than FB. Then it will not grow out so through undeflected, and it will most likely crash on the right-hand side of this plate. So let's move forward. Okay, I think I have some messages in the, let me see, messages I have in the chat box. Please, what is the name of the YouTube channel? If you go to the LMS page, you can get the link. You can just get the link of the YouTube channel and just click it straight away from it. Or you can search my full name, Olubenga Oshakwade, on YouTube. Should see it, should that too. And I can see, can you please explain the application of velocity selector? Okay, let's look at another example. We would have to talk about velocity selector before we conclude this. So I suggest you pay attention. Okay, this Bainbridge mass spectrometer. It separates ions according to their mass to charge ratio by first passing the beam of ions through a velocity selector and then passing the beam through a second uniform magnetic field that has the same direction as the magnetic field of the velocity selector. Now, this is the velocity selector. We have seen this before. And this X signs here, they show us the presence of magnetic field. And the direction of this magnetic field is in the direction with which you are looking into the screen. The direction with which you are looking into the screen is the direction of magnetic field. Now, this velocity selector, the work is to ensure that whatsoever is entering this arena has a certain velocity. That is its work. And how does it work? It works by, for the fact that the charged particles are in motion, they possess magnetic field. And for the fact that they possess magnetic field, they will respond to other magnetic fields. They would respond, meaning that they will experience magnetic force as a result of other magnetic fields. Now, this charged particle is moving through this channel. It's moving upward in your screen, and the magnetic field is beaming into your screen. As magnetic field is beaming into your screen, it means that the direction with which this charged particle is moving is perpendicular to the magnetic field. Being is perpendicular to being. So that means it will experience a force, not just a force, it will experience magnetic force. And the magnetic force it will experience, it will point in this direction. Magnetic force. For the fact that these are conducting plates, where electric field has been set up, there is potential difference between these plates. Electric field has been set up between these plates by setting up potential difference between them. Electric field has been set up here. You can see the direction. This is the positive plate, this is the negative plate. That is why the direction, these orange lines are electric fields pointing to the right. For that reason, because a charged particle is coming here, a test charged particle, like let's say a positive charged particle, we would expect it to move to the right. So, and for that reason, we should experience FE. FB, FE, they are both vectors now. So FB is experienced, magnetic force is experienced to the left, while electric force is experienced to the right. This is still a velocity selector. What we have here is still a velocity selector, and it has been fine-tuned such that only charged particles of certain velocity should go through. When a charge particle of low velocity let's say when we say a certain velocity, FE has been fine-tuned with B such that when velocity V goes through, it will go undeflected. So when we have a charged particle whose velocity is greater than the desired V, it will have a bigger FB. And when it has a bigger FB, it will tilt to the left. It will not go out through the slit. When it is slower, when the particle coming in here is slow, the FB will be very small compared to FE. Therefore, FE will pull the particle to the right, so it will crash into the right plate and it will not go out through the slit. So the condition that will make it go out through the slit is when its velocity creates a magnetic force that is equal to the constant electric force here. So let's put that. So once it enters this region, there is no more electric force. There is no more external electric field there. So the charged particle will come in here, and what it will experience within this region will be magnetic force. And as we know, like I've written here, that magnetic force in this scenario is pointing to the left, while electric force pointing to the right. But in this place, there is no electric field anymore. So once it enters this region, the next thing that it will do, it will travel to the left because there is nothing pulling it to the right any longer. So since it's traveling to the left, it will curve and crash into this disk at a certain point P. So where it lands depends on its mass to charge ratio. Where it crashes into this point depends on its mass to charge ratio. So, and that's being explained here. The mass to charge ratio is explained here to be the formula we have for magnetic field earlier, where we said B equal to MV over QR. I think we have this formula before. When you play around with it, you have this. And we have also played around saying QE equal to QVB. Where we say Q cancel Q, then we can now say EV rather equal to E over B. So V here is replaced with E over B for us to now have this final expression. So the mass to charge ratio is what, so before we move on, B not in here, B not in here is the is the magnetic field applied still in the same direction like B in. B in was applied in the velocity selector, while B not in was applied in the region where we don't have electric field. And right there, when we have, let me clear the screen, when we have a large mass to charge ratio, then that means the radius R we have here will also be radius R. This is the radius R here. The radius R we have here will also be large. But if it has a small charge to mass, if it has a small mass to charge ratio compared to what we already have on the screen, it's going to form a smaller semicircle. If it's a large one, it will have a larger semicircle. So with this device and the application of electrodynamics of charged particles, then we can say that it can be used to determine, it can be used in applications like mass spectrometer, velocity selector, and also the cyclotron. I've put this on the LMS page, so I suggest you go and read through the applications of the cyclotron and also the use in galvanometer. We've spoken about galvanometer several times in this class, especially while talking about the Wheatstone bridge and the potentiometer, the meter bridge. So the galvanometer, I think the time is up. Let's continue from here on Thursday. So on Thursday, we'll continue from here, and we'll also talk about magnetic fields and magnetic forces off and on current carrying conductors. So see you on Thursday.